So my understanding was that since there are four lecturers in a day and it's late, so it's reasonable to have some kind of easy listening lecture at the end. And so I'll try to be to start with at least with easy things, and maybe I even will start with something which is more like classical information theory. I think it's of course Kolmogorov complexity is a great thing, but if you don't know what is Shannon entropy, probably frankly speaking, first you should learn what is Shannon entropy. So let me start with some kind of very easy questions. And okay, first question is everybody will solve it immediately. So imagine we have some number x, which is between, say, I don't know, 1 and 1,000. And you need to guess this number, and you're allowed to ask questions which have answers yes or no. So how many questions do you need? 10? 10. So what you will ask then?
More than 500.
Yeah, so you will start with all the possibilities between 1 and 1,000, and you will first divide it by half, and divide it then by, then you know in which half it is, and then you divide this half by into equal parts, and you know in which half it is, and so on, until you find the things exactly. So 10 questions is enough. Okay, so, and who can explain why 9 questions is not enough? So number of possible answers. So what is this number?
600.
So if you have, so for each, imagine you have, why 9 is not enough. Imagine you have 9 questions. Questions number 1, questions number 2, and question number 9. So for each number from 1 to 1,000, you can just see what will happen with this, wow, with these questions. So you say yes or no, or something like this. And then, since there are more, only 500 combinations and 1,000 numbers, there are 2 lines which will give the same pattern of the answers. So in this case, it's not possible to distinguish between them. And so if your algorithm, which claims to guess the number in 9 questions, in one of the cases it will be necessary false. It will give the same answer for both cases, and in one of the cases will be a false answer. Okay, so 10 enough, 9 is not enough. Now next question. Imagine we have 10 questions, but we need to give the list of questions advance. So there is an online model. So you first ask whether it's bigger than 500. Then you know that it's bigger than 500, and then you compare with 750 and so on. But imagine you want to have the list of questions in advance. So can you do it still in 10 questions or not? Yeah, what should you do? Sorry? Yeah, so the question should be very simple. What is the first bit of binary representation of x? What is the second bit? And so on. Okay, so still you know all the answers. Let me ask a more complicated question. Imagine that we are allowed, not we who are guessing the number, or the person who answers the questions, allowed to make one false answer. So imagine that you may the person may lie, but only once. So how many questions you need then?
30 is enough.
30?
Is enough.
30 is enough. Why 30 is enough?
You ask each question 3 times.
Yeah. So if person can lie only once, it's easy. There is easy interrogating technique. You can ask the same question 3 times, and by majority you know the correct answer. So you repeat, 30 is just 10 times 3. Okay, so 30 is enough, and 29 is enough or not? Enough. Why? Okay, let's make a kind of auction. So 30. Who knows better? Yeah.
I know that bread exists.
So you know what?
That bread exists.
23.
23. Okay. Why? 23 is enough.
Because we can ask twice if answers is the same.
So you ask twice, and if answers are the same,
We ask
we don't need to ask third time.
yes.
So if I'm very lucky, we have 10 questions, and if we always have the same answer for these two, ask each of them two times, so we have 20 questions. But there is a bad case when we ask some question and then the answer are different. So in this case, we need one additional question, but actually we don't need to ask 2 questions later. So we have some savings. But still, if this bad question is the last one, we still need one more. So your nice suggestions can be even improved, and we see that 21 is enough. Okay, and also we know that, for example, 9 is not enough because it's not enough even without false answer. Sorry? Okay, so there is another kind of auction. We can improve the lower bound. So you say that 10 is not enough. Why 10 is not enough?
Imagine the answer of the first question, no matter if it is always 1.
Yeah.
So it's 9 question.
Yeah. Of course, you can decide in advance that first question you will always answer 1. It's a good. So then this question has no information. The first column is always yes, and so we can still we have essentially we have one question less. So 10 is not enough. Okay, now we have 10 is not enough and 21 enough. Okay, let's make what is complexity theory about making the lower bound equal to upper bound. And you know that it's very rarely possible, but actually in this case it is possible. So let's continue. Who can do better in any directions?
Can we ask which number of questions was false, if there any?
No, no. We can. No, there is no forbidden topics. You can ask about anything, but what you ask should be yes or no question. So you can say whether you lied at position 1, or whether you lied answering some of the questions, or whether you lied answering one of the even questions with even numbers or with odd numbers or whatever. But what?
15 is enough.
15 is enough. So somebody knows how to do 14. Okay. So why 14 is enough?
You can ask where the wrong answer between first.
So first, say it again. So first we ask 10 normal questions.
Yes, and then we ask.
So we ask 10 normal questions, just going back and forth, like here, making the division. Yeah? And then?
We ask, is the number of wrong answer, is there a wrong answer with the number, with index more than 5?
Okay.
And then we ask.
Okay, then you try to find the wrong answer. Which answer was wrong in by the last part of the questions. So, but there, it's a natural idea, but there are obvious problems. What is the obvious problem here?
There was no mistake.
So there are several things. First, maybe person never lied.
But they ask, is there a wrong answer?
Yeah, okay, you can get some, but you know that the person can lie, postpone the lie to the second part. So you are in a kind of complicated situation because you don't know whether he like in many stories, you don't know when somebody tells that he was lying, you never know whether he is lying now or he lied before. So there is also another problem. Another problem, imagine that first we asked about 500, and then we make all the answers about 750 and so on. And then after all this, we find out that the first answer was wrong. Then what is the point of all the subsequent questions are not very useful after that.
But we can ask about bits.
Okay, so we can ask about bits. So 14 is still under question, not clear. So can anybody provide explanation why 14 is enough, or? Yeah.
I think I can. We can do a
Please. Sorry?
We can do a canon code.
Oh, this is theory. Okay, so please explain how you do this.
I mean,
So let's write this. It's Hamming. Whoops, doesn't work. Hamming code. Okay, so what is Hamming code?
well, we would refer to the stream of 10 bits, which encodes the number x itself. Then we would basically find 2 to the 10th or string of length 14, such that balls in the Boolean cube not intersect of radius 1.
Okay.
It's kind of
Okay, balls in a Boolean cube don't intersect, and they are constructed by Hamming code, and this is 14.
yeah. Okay, I can make it explicitly.
Okay, let's just make. So who thinks that he understands this proof with Hamming code, Hamming balls, and so on? Okay, can you explain this? What he's saying more clearly?
Oh, well, I can explain what is Hamming code.
Okay, what is Hamming code?
First of all, this is a code that having a distance 3, it means that every 2 words in this code differs at least at 3 positions.
Okay, let me just write it. So it's possible to have, for each of the numbers between 1 and 1000, it's possible to write some string of length 14, yeah? What do you want to write? 14. Because we claim there are 14 questions. And ask about bits of the strings. So instead of using just binary representation of each string, we use this new Hamming representation, whatever it is. But the main property is that if we have 2 different lines, they are on distance 3. What does it mean? That they differ at least in three places. So there is not. So they are all not very close to each other. For each 2 strings differ in 3 places. And you claim 2 things. First, that it's possible to find the strings. So it's possible to find 1000 strings of length 14. This is claim number 1. And the claim number 2 is this is enough to make correct questioning. So who agrees with claim number 2? That this is enough for... Okay, just say it again. Why it's enough to have such a thing? Its code. Its name is error correcting code of distance 3. Why it's enough?
Because if the resulting word given by the person we asked differs from the correct word for the encoded word in one position.
So the questions are the same. We ask what is the first bit of this code, yes. What is the second bit, but and we get some answers.
Not for the source word.
Yeah. So we ask now about not about binary representation, but about just bit of this Hamming encoding. And so we get 14 answers. And we know that these 14 answers are only one of them is incorrect. So it's this thing should have distance 1 between this thing and one of the words. And
that 1,000 words each have distance 3.
yeah, so if it's close to different things, if there are 2 candidates, this will mean that we have 2 things which are on distance at least 3, and there are. So we change 1 bit and change another bit and change more than 3 bits. It's not possible. So if we have an error correction code with distance 3, then we are okay. But the question is how to construct this error correcting code. So who knows? So sorry. So let's check. So imagine we have this code with distance 3. Is it clear why we can guess this thing with 14 questions with 1 false answer? Please raise your hands who thinks she understands this. But maybe you can ask something, because I see that there are.
I think I've got another solution for 13, or at least another solution for 14.
For 14.
Using the Chinese remainder theorem, you can just ask about residues modulo co-prime numbers, and then divide and conquer on the possible residue as well. And you just
Okay, actually, first I'm not sure that indeed it will give 14, but I want to finish with this argument. So imagine we have this error correcting code. So we have 1,000 strings of length 14, which are different in 3 places. And then we agree, we show to ask questions, we show the list and ask, look at the table and look at your number and look on the correct string which is near this number. And what is the first bit? And then you ask what is the second bit, and you get 14 answers, which are almost one of the line in the table, except for 1 position. And then you try to find a line in the table which is close, and this line is unique because if there were 2 lines, they will be too close to each other. This is a scheme of the proof. And please raise your hand again who believes that he or she understands this argument. But okay, but maybe somebody can ask, because I don't know what is not clear here, or maybe somebody can guess what is not clear and explain this, because I frankly speaking, I'm lost, because it's I cannot.
Maybe we should just construct it and show it, and you can't.
No. How to construct is another story. But before constructing, I want to be clear how this code is used. So we haven't constructed yet. We just imagine that it exists, and then we say why it's enough to.
Well, I believe it can help if you show it on a small example. I mean, I can show the string.
Okay, let's illustrate the thing with 3 questions. So imagine we have only 2, we should guess 1 or 2. And then there is a very simple code with distance 3, 0, 0, 0, and 1, 1, 1. And so what we do, we ask first bit, second bit, and third bit, which means that we ask 3 times the same questions. Is your number 2? Is your number 2? Is your number 2? And then we get some answer which either are completely correct, so we can get either 3, or we can get 2 1s, or and then these are close to this one, and these are close to this one. The distance is 1, and here the distance is 3. So there is no chance to mix things with each other. Okay, so maybe somebody can ask some specific question, no? Okay.
Why is distance 3?
No, how to construct this code, or why we need distance 3.
Yeah, why we need distance 3?
No, imagine, okay, I didn't claim that we need it strictly, but the problem is, imagine we have distance 2 only. Then there are only 2 places when, oops, it's kind of strange thing. Then we have only 2 places when things are different. So imagine we have something which coincides with this in one place with this thing, and another place coincides with these things. And then we have a dilemma, whether the correct answer is this, but we lied in this place, or the correct answer is this and we lied in this place. So how do we know? So distance 3 is reasonable to have, at least. Okay, so then there is a specific thing, how to construct error-correcting code of distance 3 for 1,000 different objects and length 14. So who knows how to do this? Please raise your hands. No. Who really knows? Not just remember that there is some matrix which is called Hamming code matrix, and just seriously knows. Yeah. So
I just write unary matrix with stem columns, and I repeat once such they will coincide as an example above.
So sorry, I don't. So what do you say it again?
So I use the first column like a column of unary matrix, but the
first column of what? Unary matrix, same times 10? Okay, I don't really understand what is this. Okay, so you write here 0, 1, 0, 0, 0, 0, yeah?
Yes. Then I write 2 ones above the first one.
2 ones where?
Above the very first one.
Above the very first one.
So I obtain the first column of my table. Then I shift these 3 ones up below.
Like this.
No, not like this.
Okay.
Yes.
So like this?
Yes. So I write 1, 1. So and so on.
And like this.
Yes.
But it's very soon everything, it's just one, actually, if you have 10 by 10, you have only one more thing. So what? Why it's happening? Why it's... Okay, who really knows what the Hamming code is? Is there anybody? Okay, just say it again. Okay, let's delete this stage matrix.
This option of construction. We want 14 positions of a word. We just write, right?
Yeah, we want strings of length 14.
Yeah, 14. Yeah, we just enumerate them. Write down 1, 2, 3, 4, and so on.
Very good. 1, 2. It's even I can do this. 4, 5, 6, 7, 8, 9. If I should count in French, it would be more difficult. But I think in English it's easy. From 1. From 1. Okay. So.
Then what I will do is I will show how to encode every string of length 10.
So every string of length 10?
I will transform it into a string of length 14.
Okay, so instead of encoding numbers 1, 2 to the 1,000, of course we can encode every string of length 10 because there are even a bit more of them. Okay, so how do we do this?
Well, I just write down the string I want to encode into this position.
Okay, but there are more positions.
Yeah, but I will omit positions which are exactly this.
So I just write up to this, yeah? No?
I will write it. I will omit. I will leave blank.
Yeah, let's leave blank some position. Which?
I will leave blank positions which are powers of 2.
Powers of 2. So it's 1, 2, 4, and 8.
Yeah. In the rest of positions, I will just write the string.
Okay, you can do even more strange things. Why not? x1, x2, x3, x4, x5, x6. If we are correct, everything should match. Let's try. Oh, great. Surprisingly, everything is okay. Yeah. And you will keep them. So the idea is to keep them here and just add something on positions 1, 2, 4, and 8.
Absolutely.
Yeah. So what do you add there?
Then I would just want to fill out the rest positions. To fill the position 1,
Yeah.
I will add modulo 2 some of the bits that are already there.
Okay, which one?
In this case, that would be bits number 3, 5, 7, 9, 11, 13. That is the numbers which have 1 in the last bit in binary notation. Right.
Yeah, there is also number 1.
Yeah, but so if you put the dot in here, then it would mean that the sum modulo 2 will be equal to 0.
So we want this sum modulo 2 to be equal to 0. And if I'm there theoretically should be a possibility to write a special another. So let's see this. Okay. So this is the bit which we determine, and by this equation. So this is okay. So why not? Let's try. What we'll do next?
Then, well, we write basically the next equation.
Next equation.
Yeah, this is another sum modulo 2.
Yeah, which things are included?
We include positions which have 1 in the second least significant bit. That is 2.
So I see that you want me to write things
Right. Exactly.
just each column number should be written in
Yeah. Well,
in
we actually
binary.
if we don't want this table, we can omit it. We just, I mean, it's 2. We use 2 positions, we omit 2 positions. We use 2 positions, we omit 2 positions, and so on and so forth.
Okay, let's 16 is 8 plus 4 plus 2 plus 0. So first of one was positions where we have 1 here. And the second one will be the positions which have 1 here, which is what it is.
2, 3.
X2.
It's not exactly x2. It's
Yeah, just position 2, position 3, 4, 5 are empty, position 6, position 7, 8, 9 are empty, 10, 11, 2 empty, and this last one.
yeah. So basically, for the number 4, we just mark 4 positions starting from 4. Then we omit 4 positions. Then we mark 4 positions, and so on.
And again, we want to add them.
Yeah.
Add them modulo 2. It should be 0. And again, there is one. Okay, let me try again this technology. There is one which is not yet defined, and all other are defined.
Right.
And so we can do the same for 2 other lines. Okay, so let me ask. So do you understand the principle? What should we do? So who can say what should we do for the 3rd line? Okay, but I see. Okay, what should we do for the 3rd line?
XOR.
XOR of what?
Second line.
XOR things corresponding to this line. Okay, no, it's not the right
Not
one.
this.
The line which is, I think, the 3rd bit from the right.
Third
Yeah?
line, yes.
So it should be this. So it should be 4 and
When 3 blank.
4 blank, I guess. And then,
Again 4.
okay, and the last one will correspond to the things which are having the last bit, which are this one. Okay, so this is a very peculiar thing, but then we probably understand what is happening, but why it's a good idea. Can you explain how this helps?
Yeah, I can, but I think I won't use the word distance between these words. I'll just show how it works.
Okay.
So basically, we ask the guy.
So you will just explain. Imagine we have one of the. So we now have the sequence of 14 bits. We fill this position somehow, and now we have sequence of 14 bits. Now we change one of the bits, and you want to find how to reconstruct the original sequence. So you don't explain why the distance is 3, but you define the mapping from these balls, from the change things to the original things. Okay, how do we make this error correction?
The error correction here is very, very simple.
Yeah.
Suppose that this guy who answered our questions, who wrote this adversarial string, he changes some column. Basically, he flips some bit.
Yeah, imagine that we have a correct string, and one of the bit, I don't know, bit number 6, is changed, is wrong.
Yeah, so then let's have a look how the string, what's wrong. We see that all the equations that we wrote, some of them become false.
Yeah, since we changed one of the bit, now the equation become false, and not all the checksums are 0, and some of them are 1. Yeah, so what?
So basically, if we just have a look at what equations become false, we immediately see that just because of this construction, if different positions were changed, different subsets of equations become false.
Yeah, for example, if we change position number 6, then the equations will false in the cases when, in the things where we have ones. Yeah. So second and third equation will be false, and so instead of 4 zeros as a checksum, we have 0, 1, 1, 0, right, which is exactly the number of the bit which was changed. Yeah. So it's kind of even what you do is somehow better. You just give a very simple algorithm how to make this error correction, because theoretically, even the distance is 3. Maybe you need just to test all the possibilities. But here you just very simply you compute these 4 things, and then you can get exactly the bit which is.
Then we basically get this wrong bit right, and then we drop all the unneeded bits, and we have our string of bits which we originally wanted.
And actually, we can use the same for 11 bits encoded in 15 bits. And you can also guess, but we can do the same for 31 bits. And then we need 5 control bits. So we have 26 to 31, and so on. And this is called Hamming code. Okay, so I am now afraid to ask, but still, who understands now what is Hamming code and why it has the error correction of 1 error? Maybe somebody can ask question. No?
Am I correctly understand that if some of the answers will be false, we will have some kind of dislocation in more than 2 places?
No, so there are two things. So we can now forget actually about answers. What we say, that imagine we have a string which has this 4 checksum 0. And then we change 1 bit. Then we know how to find which bit was changed. So this is the Hamming code. This is independent of all the story about liars and so on. It is just a combinatorial thing. Actually, you can, later. So, and this code can be used then for our answering strategy. We just ask the person about the bits of the Hamming encoding of the number. So if the person says everything correct, we have a 0 checksums, and we know this. Because if the person makes 1 false answer, the checksums will not be 0. We know that the checksums will just give us the binary representation of the number when we made a change. So this is. Okay. Any other?
We still need lower bound.
Sorry?
We still need lower bound.
And you have it?
No.
Yeah. Okay. So this is. Let's if Okay, let's think. So we see that 14 is indeed enough. So this is good.
Lower bound, I think. So
So let's play according to the rule. So you think you believe in some lower bound. What is this lower bound? 13, 12, 11, 10 is already bought, so you can sell us only 14. So 14. So 13 is not enough, let's say. In this, so 13 you claim is not enough. Good. Why 13 is not enough?
Because we need 10 bits for the word and more than 3 bits to encode the location of the error bit.
It's kind of philosophy. Indeed, we need somehow, but maybe we can combine them in some way that blah, blah, blah. No? So who can, or can you say exactly why 13 is not enough?
No.
Okay. Who can explain why 13 is not enough? No. You are disqualified. No, definitely not. Okay.
Maybe because we have a space of dimension 14, and we want to place balls of size 3, enough balls.
Let's see. How, we have space of dimension 14 over
Z1 or Z2.
Z2, but okay. But okay, we admire your algebra background, but to be simple, we can say that we have 2 to the 14 combinations of zeros and ones. Even people who don't know algebra can see this. Okay, and so we want to make something, to make disjoint balls of distance 1, of radius 1. So what is error code? So if 2 things are on distance 1, they cannot be the same. So how many things we have in one ball of distance 1? We have 1. 5? So we have a string of length 14. What is a string on distance 1? It is just the same string with one thing changed. So we have 14 places to change, and also we can not change anything. So ball of radius 1 has 15 elements. So now it's a very important computation. So we should multiply. We have 1,000 balls. Imagine we are able to put 1,000 balls inside this space. So to find 1,000 strings of length, no.
Maybe we should replace 14.
Yeah. Then we will, no, we should want to show that 13 is not possible. So balls of radius 1 now have 14 elements. And so there are 13 positions. So we should multiply the number of balls, desired number of balls, on the volume of each one. And this is 13,000, and this should be enough. It should be less than the size of the space. We should have enough space. So it's 2 to the 13. And no, by 14. No, we want to show.
The volume of the ball is 14, so.
Oh. Yeah. The volume of the ball is 14. So it should be less than 2 to the 13th. Whoops. And 2 to the 13 is just about, it's I think 1, if I remember correctly, the powers of, okay. So we see that ball of, we cannot place that many balls of that size. And so we proved that 13 questions are not enough. And okay, who understands this proof?
I would say we need to formally claim that the
Okay, but actually, this is a proof for Hamming codes.
Right.
And you should be careful. We know that our Hamming codes are enough for questioning strategy. But theoretically, our questioning strategy is not necessarily of this form. For example, this questioning strategy is offline, so we know the list of questions in advance. But theoretically, maybe we can still make 13 questions, but ask them sequentially. And then this argument with balls is no more valid. But how to correct it? What should we? How can we correct the argument? Imagine we have the online questioning and still 13 questions.
Yes, so it's still correct. So it's still for each number you have a sequence of answers.
You can write down the sequence.
Yeah. So we can have 1,000 people who have in mind one of the numbers: 1, 2, 3, and 1,000. And imagine each of these persons, we made 13 clones of it, or 14 clones actually. And each of the clones decided at which question he will give a wrong answer. So we have 14 strategies for our adversary. Oh, actually, there is strategy not to lie also. So there are 14 clones. One is a good clone, and there are 13 bad ones which make wrong answer at some point. And then we apply our algorithm to each of these. So we have 14,000 different adversaries. And we apply our algorithm to ask for questioning each of them. And the algorithm should first find the number correctly. Moreover, if after the number is found, then we know what should be the answers, what are true answers. So we know which of the answers were wrong. So in this strategy, we can distinguish, our questioning algorithm can make a distinction between every two combination of these things. So we still have the same bound, same contradiction that after asking 13 questions, we can distinguish one of the 14,000 possibilities. So still the 13 questions are not enough, and here we have an exact thing. Yeah?
And what would we do if 1,000 would be replaced with 530? Then our proof will not... 530? 13. Our Hamming code needs also 14 bytes. But our proof of lower bound will not be correct.
No, I don't know. I don't claim that in this way we can get a correct. I think maybe one should think more, invent something. I don't know the answer now, but maybe it's possible to get an exact bound. But actually, anyway, if we increase our game, if we generalize our game and allow, for example, 2 bad answers or 3 bad answers or 5 bad answers, then we have error correcting code which should correct 2 errors, 3 errors, and so on. And for these things, there is no general answer. So there is an entire theory which is called coding theory, and the extremely clever people worked for many years for this, and they still don't know, they don't have a good bound how many code words you can have if you want to correct given number of errors. There, as usual, there is an upper bound and lower bound, and they are significantly different. So and they try to invent better and better codes, and sometimes they succeed, and so on. So it's a huge theory, and no answer is known here. Okay, so I'll try to finish this thing with one problem, very nice problem, which I heard recently from Peter Gutsch, and I just will put some specific numbers, and you will, and maybe somebody will solve it immediately, but if not, I'll just let you think about this. Imagine that we want guess a number between 1 and 1 million x. Then we have 1,000 questions, and we have at most 100 lie. So there are at most 100 wrong answers. So the distance is now 201. And to make it so of course you can say that people who know coding theory will have an advantage here, unfair, because it's a question, in this form, it's a question about coding theory. But let's say, to make it more interesting, let's say that questions should be of form x greater than something, so you cannot ask about the bits. But you have an online situation. So you can ask, for example, is x greater than 500? And you can repeat this question many times if you want. And then you can ask about some other number and some other third number and so on. But still, it's not clear how to proceed, because there are many lies. So you need to know for sure some answer. It seems that you need to ask it 101 times. And of course, if you ask, if you need actually you need 20 fair questions, and if you want to ask each of them 100 one time and one time, actually even more, because you need to like 200. So you have much more than you can. But still, it's possible, and this was invented by Peter Gutsch. And there are even another nice algorithm, different from what Peter says, which was explained to me by Kostya recently. And just you can think about this. And if somebody knows the answer today or tomorrow or the day after tomorrow, we can discuss it. But it's not. It's very, very funny algorithm and nice reasoning. Okay, so this is a combinatorial information theory, and combinatorial information theory, it's actually one line, and one of n possibilities needs, so we need log to n and questions, or log to n bits of information. And there are many things. Probably I try to select something which is not very well known, but there are classical things. For example, if you want to sort n pebbles of different weight, and you have a comparator, so you can compare two of them, find. So you have n, or you just want to sort n numbers, but the only operation you are allowed is comparison. So how many comparisons do you need? So who knows the answer? N log n. Why? So why not more? Why it's enough? Or why actually it's not n log n, but something proportional to n log n? So why it's not can be less? This is information bound. Why it cannot be less?
In places on n
places of that bits.
Sorry? We have n numbers.
Because n numbers, so we need, for each number, we need to show its number in a series.
We need to find its place.
Find its place.
Okay.
And to encode the place, we need a logarithm n.
Yeah, but they are not independent. After we encoded places for all numbers except 1, we don't need to encode the place for the last number. So it's not exactly. Yeah, so there are n numbers, so there are n factorial possible answers. Possibilities. And so we need logarithm of that. Logarithm of n factorial is log 1 plus a log n. And one can see even without integration that the second half, there are n over 2 numbers which are greater than log n over 2. And always something about n log n over 2. So if we have one of the log n factorial possibilities, then there is no chance to use less questions. And there is also an upper bound, why it's enough. And this, everybody who studied algorithms knows that there are several n log n algorithms for sorting. Actually here, things are simpler because we can't only count comparisons. So we can just sort by insertions. If we have k elements, we need to place the new element among them. And this requires log k comparisons. And so it's less than log n. And so total number of comparisons is n log n. But if we just make comparisons, there are also shift operations. So if we count everything, it will be not a good algorithm. But if we are interested only in comparison, it's okay with this. So this is what is called combinatorial information theory, so to say. It's not a theory, but if we have some bound for the number of operations due to informational reasoning, often it's like just this simple thing. So you need, if you have n possibilities, you have n bits to specify one of them. Okay, so this is combinatorial things. Another thing is probabilistic. So there are three things. It's combinatorial, probabilistic, algorithmics. And probabilistic, oops, wow. Yeah. So that's a good question. When we should stop, actually? So there is a place for reception. So it has priority over everything. Yeah. When it will happen?
7:15.
Okay, so should we make a break? What do you think? Or yes. At least if at least one person wants, that's unavoidable.